Welcome to the Jack Westin MCAT podcast with your host, Phil Hawkins.
And Azaii Calderon-Muñiz.
All right, it is the best day. It is Physics Day. We're going to talk about some physics stuff because physics is coming up in pop culture, and that's exciting. I was just telling Azaii, I think physics is becoming cool again. She's like, I don't know why I'm getting these like interesting articles about physics. And I'm like, that's because physics is cool. But today we're going to be talking about nuclear physics because of the Oppenheimer movie. And I am super excited to talk about this because physics, specifically nuclear physics, is on the MCAT. It's something that they like to test students on. It's also an area that I think students tend to neglect because they're way more worried about like optics and things like that. But even then, I feel like the MCAT has tested some of these things more than they have in the past couple of years. As a matter of fact, if you asked me a couple of years ago how much about what we're talking about today in this podcast, how much of that do you need to know? My answer would have been very different than it is today. Because things have been kind of popping up a lot more with like the strong nuclear force and weak nuclear force. We'll talk about more of those here in a second. But I am super excited to talk about this because we get to talk physics.
Yeah, like you said, I've been getting all these, I've been getting a couple of physics articles, and I was just like, I think my phone is listening to our conversations because I primarily have these conversations with you. But yeah, I think it's like you pointed out, the movie, the Oppenheimer movie, is really what's getting people talking about these things. And, you know, one of the pieces that I read was about nuclear fusion. Another one was about the energy coming from the sun. And there's so much woven into the movie. I actually haven't seen it yet. I don't know if you have.
I'm anxiously awaiting.
So we can't spoil the movie for anyone if anyone is concerned about that. Do you have any favorite fun facts about Oppenheimer? I feel like
I haven't seen the movie yet. I do think I could spoil it though, because I know how it ends.
I meant the person.
Yes. The person Oppenheimer. I mean, super interesting person actually. Yeah. But that's like super, like I want to go down that fun fact rabbit hole because Oppenheimer was kind of an interesting person who like started off in theoretic and then got pulled away into practical, and it's just kind of an interesting trajectory. He actually really hated theoretic physics and like was writing about like, I hate physics and I'll never be a good physicist, and like writing letters to people about because he was not in a good fit for his job. That's a good thing. People think about your specialties, not that you need to, but I'm just like thinking about that. There is some connection there.
I feel like I always learn something new with you about the different people involved in the science and psych-soc in ChemPhys. It's really fun just having those micro-learning moments and pop culture moments. So today, before we start talking about reactions that happen at the level of the nucleus, it's really important to take a step back and just think about what are the main forces at play in life, right? Specifically from a physics perspective. And we're going to talk about 4 of these fundamental forces that you really need to know for the MCAT. And the first 2 are ones that you are probably already familiar with, and for the MCAT need to be incredibly familiar with. And so those first 2 are gravity, and so the gravitational force and the electromagnetic force. And what might be, I know for me, what was surprising to learn about these 4 forces when I was studying was that the gravitational force is actually the weakest, which is truly wild because you think about how the gravitational force is what holds us where we're sitting, right? In our case, sitting wherever you might be, if you're, at the gym or on your way to work or something like that. It's what's keeping you from flying, off the earth. But it's actually the weakest. And it's reliant on a few different things. It's reliant on the distance that 2 objects are from one another, as well as their mass. And so often we think of the gravitational force. We have a very short equation for it, but you do have to be able to conceptualize how the distance will affect the gravitational force and recognize that it's not a 1-to-1 ratio, right? So it's not just if I'm, 5 meters away, it's the radius and the distance is inversely proportional to, and I didn't specify that, inversely proportional to the gravitational force. But it's not just by a factor of 5, right? And so there are little things like that even if it's not plug and chug, the MCAT can test you on. So knowing equations for physics is incredibly important, incredibly high yield. As a quick plug, equation sheets with units and examples can be really helpful for a lot of students. And so having the equations for the gravitational and electromagnetic force can be helpful to conceptualize what's happening, be able to see how they can test you. Even if it's not plug and chug, they expect you to be able to take some value and square it and see how, by what factor something would change. So in terms of gravitational force, that's something that they could do. The electromagnetic force is therefore stronger because I just said that the gravitational force is weakest. The electromagnetic force is stronger, but even then, even though it can apply over longer distances, we don't typically see it applying over huge distances. And that was something else that for me was a little weird. So thinking about why this is the case, unlike the gravitational force, which is just between any two objects with mass, the electromagnetic force requires some kind of charge, right? But if you think about it, if you had a giant, sun that was just one positive charge, and then you had another one that was a negative charge, then you could have it acting this force over really long distances, but that's not typically what we see. It's pretty strong. And so charged objects and charged, ions and whatnot tend to interact fairly quickly and over shorter distances than, say, the gravitational force. And so that's a way to differentiate the two, but recognize that they're two incredibly important forces you need to know on test day. We just have different reasons, even though both can act over longer distances compared to some of the other forces we're going to talk about. Different reasons why one does and one doesn't seem to as much.
It's really interesting. We're talking about the 4 fundamental forces of the universe. Like, as far as I'm putting an asterisk here, as far as we know, there are 4 forces to the universe. I might talk a little bit more about that here in a second. But really, when we think about like day-to-day life, it's these 2: gravity, electromagnetism. That's it. Every force that you are interacting with on a daily basis is one of those 2. I always have students like, wait a minute, what about buoyant force? What about normal force? What about tension force? What about all those other forces? Actually, all of those are really specific applications of electrostatics, right? Like, what stops my water bottle from going through my hand is the electrons in my hand and the electrons in the bottle are repelling each other. And that repulsion stops them from moving through each other because atoms are mostly empty space. And so they should be able to like pass through each other, like 2 like flocks of birds could like pass through each other, or galaxies pass through each other like they do. I like what you were saying about just like, we don't have these giant things with like giant negative charges and giant positive charges. And that's a part with just how the nature of how electrostatics works, where like mass always pulls together. But if you have a bunch of positive charges, they're not going to pull together into a clump and have a giant positive charge. And so that just doesn't work, right? Because positives would repel. And so we don't have those like large, giant forces that pile up. Like the entire Earth is a big pile of mass. It's not going to be a big pile of positive charges because they would all like explode and repel each other because they're so strong and the repulsive forces would counteract. But if you had asked me, and this is something that I have talked about a couple of years ago, that when it comes to the MCAT, it's really just about those 2 forces. And I actually really encourage students to think about electrostatics in the context of gravity because they're very similar equations. The forces for gravity are KQQ over R squared. I'm sorry, GMM over R squared, G being a constant, M being for mass. For electrostatics, it's KQQ over R squared. So it's like the same setup even. It's like constant times whatever we're talking about, either charges or mass over distance squared. And so I find, and this is why in the course I talk about gravity and electrostatics together, because I think gravity is just really intuitive for people because, like, you know, you roll out of bed, your feet hit the ground, nobody's surprised by that. But like, why is that magnet floating, right? Like, that's magic, right? And so electrostatics is a little bit stranger, but if you think about gravity and just kind of connect it, all of a sudden it's like, oh no, that of course that's how it works, because it's kind of like gravity, only it's like a couple of small differences in there. But let's move. Oh, go ahead. You have something.
I think I could be very wrong, and I actually never got into magic tricks. But I'm just wondering how many times magic tricks are the result, like floating things are the result of magnets. I now have this question that is unanswered that I will probably have to look up afterwards. But I'm wondering
years. That's
honestly, yeah, I don't know why it took me this long to figure out that it might just be a matter of magnets. I apologize if I have ruined magic tricks for anyone else, but I just have this moment. I can't actually confirm or deny that this is the case.
Yeah.
I feel like a government official saying that.
No, magnets and mirrors. That's what it's all about, physics. Everything that's magic and amazing in the world is physics.
Love it.
But I want to shift. Yeah, I know that I said there's 4 forces. Those are the 2 that you're going to be interacting with on like a daily basis sort of thing. But that means there's 2 other forces. And these forces are the strong and weak nuclear force. And they occur only at the very small, at the level of the nucleus, as you might guess, given from the name, the strong and weak nuclear force. So if you're talking about anything, once again, in real life, day-to-day stuff that's not nuclear physics, so gravity and electromagnetism, that's it. But once you get down into like a nuclei, if you think about like a helium nucleus, right? It's got 2 protons and 2 neutrons. Like, the neutrons are neutral. The protons are positively charged. And they're like next to each other. And we were just talking about how we don't want to end up with big piles of positive charges because they want to repel each other. But that's kind of what's happening in a nucleus. And so the question becomes, all right, wait, what is happening here? Why are these things here? Why are they not whizzing away from each other like they should, based on what I know from electrostatics? And that's because there is a strong nuclear force. And as you would guess by the name, it is very strong. It is incredibly strong, and it's holding those protons together. It's this force of attraction that holds them together. And it's like the strongest force here, but it's also got the weakest range. And so if we have 2 protons that are even just like a little bit away, they're going to repel. And you got to get them really close together to get them to actually grab onto each other and fusing protons to create a nucleus. You're talking about fusion energy and fusion reactors. And like, that's what happens. You take 2 protons, you get them close enough together, and they will latch on to each other. And that releases a bunch of energy. So you take protons, are also known as hydrogen. I'm getting excited and ahead of myself. And so this is a really big thing in the realm of physics and the realm of energy production, because that's actually what happens in the sun, right? Like, 2 hydrogens will get close enough together that they'll latch on to each other, and that releases a ton of energy. And that's why we get sunburns, and that's why we have energy from the sun, and that's why we have energy on the earth, is like, for humanity. All of that essentially comes from this fusion reaction that happens when those protons get close enough to latch on to each other. The thing is, and this is something the MCAT will test and has tested, those, like, to get them close enough together, they got to be moving really fast, right? Like, imagine that you have 2 bullets, or let's not make it bullets. Let's make it, you have 2 baseballs that are going to, like, have really powerful, let's say, magnets in them that repel, right? Or they're not really magnets. They're just like negative charges. They're going to repel each other. Let's make them positive charges, because then it's actually like a nucleus. This is how you can tell that I am making up this analogy as we're going through here. It has changed like 5 times. But if they have really powerful positive charges in here, and I threw 1 baseball, and you threw another baseball, they're never going to hit. They're going to get like close, and then they're going to repel. And like, if we throw harder, they're going to get a little bit closer before they whiz back away and separate. Now, if we fired pneumatic cannons at each other, then they would get close enough that even though like the repulsive force is separating them, they'd be getting close enough that they actually would be able to touch. And if we're talking about what's happening in a nucleus, then they'd be able to grab each other. And so this is why this fusion energy that gets released whenever we get those protons to grab onto each other, we have to heat up the hydrogens. We have to heat up the protons to incredibly high temperatures, to the point where, like, in order to do this on the Earth, until recently, we really could only do this by literally setting off a nuclear bomb to release enough heat to heat up hydrogens to be able to fuse. That's what a hydrogen bomb is, obviously connected to Oppenheimer. I don't think hydrogen bombs are in the original or are in the movie. I don't know yet, because it seemed like it was just the beginning and hydrogen bombs were not the first thing. I will say that this is actually one of the things they were really concerned with, was this hydrogen being able to fuse into helium when they were setting off the original, like the first nuclear bombs, because there's hydrogen in our atmosphere. And they thought that if you set off a nuclear bomb, like a uranium bomb or plutonium bomb, it could heat up the atmosphere enough that the hydrogens in the atmosphere would get close enough to each other that they would latch on and like overcome that like electrostatic repulsion, and the strong nuclear force would kick in and we'd release a bunch of energy. And basically the entire atmosphere would turn into a hydrogen bomb, and it would just be the end of all life on Earth. And like, this is something that they were legitimately concerned about. And they did tons of calculations. They're like, listen, like there's like I think there's a clip even from the movie that I've seen. It's like, there's a very small, like it's a less than 0.1% chance that this will kill everyone on the planet. And they're like less than that. And he's like, well, it's science. We're never really certain. And this was actually something that was a legitimate concern, but later on got actually incorporated into nuclear bombs. That's where hydrogen bombs come in. But all the energy on Earth comes from this. The strong nuclear force is what holds a nucleus together. It holds the protons and neutrons to each other in the nucleus. The weak nuclear force is the fourth force. And so this is also one that you need to know. And you got to be really careful with the language on this. The strong nuclear force holds protons and neutrons together. The weak nuclear force holds a proton or a neutron together. That sounds like the exact same thing when you are not paying very close attention. So I'm going to repeat this. Strong nuclear force holds the protons and neutrons together in a nucleus. The weak nuclear force holds a proton together or holds a neutron together, because protons and neutrons are made of subatomic particles, bosons and quarks and all sorts of really cool subatomic particles that we really only know because we've been able to like smash protons into pieces and look at the things that kind of fly out. And that's where the like super colliders come in, like the Large Hadron Super Collider. And this force is what, like I said, what holds a proton and neutron together. And this is also really important for some of the decays that you're going to see tested on the MCAT. And we'll talk about this a little bit more here in a second, like the alpha, beta, gamma decay. But I want you to be really careful with this, like the difference between the strong and weak nuclear force, especially on test day. You might be a little tired. You might be, a little burnt out, if you're pushing hard. And so like the difference between them is like holding protons and neutrons to each other, or holding a proton together, or holding a neutron together. And those are very different.
Yeah, I think that's such an important distinction to make. It's like between versus within, right? Yeah. Between proton, neutron, within a proton or neutron. And like you pointed out, when we're tired on test day, it's really easy to make mistakes we wouldn't otherwise make. And so having these things down packed now is worth your time. And just again, as a quick reminder, because I know a lot of times, and myself included, when I was going through physics, both in undergrad and then studying for the MCAT, which was a whole different ballgame compared to what I learned in class, our gut reaction is math, right? It's calculation, and recognizing that they can absolutely test you on this in a conceptual fashion rather than just, plug and chug. I really want to emphasize that. So you hinted at different types of decay, and you actually named the types of decay that students need to know on test day. The alpha, the betas, and the gamma decay. And so the first one that we're going to talk about is going to be the alpha decay. But first, thinking about what decay is. So like most things in life, nuclei want to be stable. And so if they are in a state where they are unstable, they have excess energy for whatever reason, they need to release some of that, you can have instances of decay. And we're going to talk about, like you mentioned, the different types. So the first one is alpha decay. And in alpha decay, you are losing you're not losing an electron, you're not losing individual, one proton or I should say positron, but that's coming up later. But you're actually losing a small collection of protons and neutrons, specifically 2 protons with the force and 2 neutrons. There we go, for an atomic mass of 4. And you do need to know the difference between atomic number and atomic mass number on test day. So if you haven't already gone and read into the periodic table and the different components of how we think about atoms, make sure that you do that. Strongly recommend. And also know the periodic table pretty well on test day and the trends that you'll see on the periodic table. This is some spreading activation, y'all. But so for alpha decay, you are essentially losing what amounts to a helium nucleus. Now, I'm specifying nucleus because I just mentioned you're not losing electrons in that. So something to keep in mind, technically that helium nucleus then has a +2 charge, and the atom that originally lost it is going to have a -2 charge, but you're actually changing the identity of that element, right? Because you are losing 2 protons, and the way we identify an element is by its number of protons. So that's something that is really important when we're thinking about alpha decay.
Yeah.
Now, part of just kind of thinking about how we can relate this to those strong and weak nuclear forces that you mentioned, we said that strong nuclear force is between protons and neutrons, and a weak nuclear force is within protons or within a proton or a neutron. We don't have that. We don't have the weak component here because we're losing multiple protons and neutrons. And so that would correspond to, if you're thinking about it conceptually, strong nuclear force rather than weak nuclear force. And the reason we want to emphasize that is because, like you mentioned, a lot of times and in textbooks, you'll see, weak radioactive decay, right? Or decay in general. But that applies, the weak nuclear force applies more clearly to some other types of decay that we're going to be chatting about.
Yeah. And that is a big deal, right? Like understanding which one applies, because the MCAT would absolutely test this. And yeah, to reiterate your fact, the number of protons, that defines the element. You adding or removing neutrons changes you to a different isotope. It's still like carbon. If you got 6 protons, it's carbon. If you have 6 neutrons and 6 protons, that's carbon-12. You have 6 protons and 8 neutrons, that's carbon-14. Still carbon though. But in this case, as you are kicking out 2 protons and 2 neutrons, you're going to weigh 4 less than whatever you were before. So if I was carbon-12 and I kicked out 4 things, I'm going to be something that weighs 8. I wanted to say carbonate, but I'm not going to be carbon anymore, right? I think I'm going to be, is it beryllium? I need to look up my periodic table. It's a beryllium. It is beryllium. It would be beryllium. So if I was carbon-12 and I underwent alpha decay, I'd turn into beryllium-8 because I'm going to have 4 protons and 4 neutrons. I do want to take a second and actually mention, though, carbon is not going to do alpha decay. The reason that we have this, so, kind of talking about that strong nuclear force, like we were talking about, it's got a really short range. It's on the order of a couple of femtometers, which that's real small, right? You go past the micro and nano and pico and eventually you get to femto. And so we're talking about real small distances. And so when you get to a large nucleus, things like thorium and uranium and stuff like that are really big, all of a sudden, there's so many positive charges in there that we have this electrostatic repulsion, but the protons are so far away from each other in the nucleus that strong nuclear force on each side is not pulling those protons to each other anymore because they're too far away from each other. So even in the nucleus, it might be they're too far away to hold on to each other well. And so what'll happen is some over, in case of stuff wiggling and moving around, something will get kind of ejected because that electrostatic repulsion, while not stronger than the strong nuclear force, the strong nuclear force has such a short range that even within a nucleus, it might not be able to hold it all together if it's a big nucleus. So I have sometimes seen the AMC ask questions on which element would be, or which of these would be most likely to do like beta plus decay or beta minus decay. They could, in theory, ask which would be likely to undergo alpha decay, and you want something big, like some with a big nucleus. It's not going to be carbon or nitrogen or oxygen or fluorine or any of those things. But it is also important to just know that if they say an alpha particle, you need to know an alpha particle is 2 protons and 2 neutrons stuck together. That's also a helium nucleus. No electrons, right? Because helium is like 2 protons and 2 neutrons and then some electrons. So it's not the whole helium that we normally see. It's just the nucleus there. But the AMC will use those terms interchangeably. Alpha particle, helium nucleus, 2 protons and 2 neutrons. Like they can word it like in any different way. And it's all going to be the same thing. And you need to make sure that you understand that kind of difference in there. So there's also the beta decays. And so beta goes alpha beta, right? There we go. Nice. I love it when things make sense and are ordered. Beta decay is a little bit tricky because it turns out there's a couple of types of beta decay. And so in beta decays, this is where we're dealing with the weak nuclear force. And so like a proton is coming apart or a neutron is coming apart and kind of like switching from one thing to another. I always remember that it's a balanced equation. So in beta decays, a proton turns into a neutron or a neutron into a proton. And it stays in the nucleus. It just changes what it was. And I remember it's balanced. So if a neutron turned into a proton, in terms of charge, I need a negative charge in the product there because like a neutron is neutral, turns into a proton, which is positive, and a negative charge. Okay, we're even in terms of charge. So that's why in beta minus decay, your neutron turns into a proton, and that produces an electron, which is also known as a beta plus particle. And it's like these names we have to be kind of careful and tricky with. Beta plus decay is the opposite. Beta plus is we have a proton turn into a neutron, so it goes in the other direction, and a positron, which is basically the positive version of an electron. It's a positive charge. And so proton to neutron plus the positron. For the most part, when it comes to the MCAT, they don't test you on a lot of like subatomic particles other than like the classic proton, neutron, electron. Positron is one that they will test you on. You do want to know what a positron is, especially since the AMC has been seeming to test this stuff a little bit more. And positrons are really important in medicine. And like every major hospital is doing stuff with positrons every day. The thing about positrons. So if we look at electrons and protons, electrons are like way smaller than a proton. An electron is like, it takes like 2,000 electrons to be this mass of a proton. So electrons are tiny. A positron is like the same as an electron. It's also incredibly tiny, but it's got a positive charge. I don't think you'll need to know this, but a positron is actually antimatter. It's an anti-electron. And so that's why it's got this kind of like opposite charge and why they're kind of like interestingly like similar together. So it's actually an antimatter thing. And so because that like electron is like the anti of that would be a positron. I think that's the only one that you would need to worry about for the AMC. But these beta decays, proton turns into neutron or neutron into proton. I do want to say this is something, so this is the weak nuclear force because we're talking about like protons and neutrons breaking apart. They will sometimes ask you which of these elements is most likely to undergo beta plus decay or beta minus decay. And so that's something that you do actually want to be able to recognize. And it turns out in a nucleus, especially at small nuclei, when you get to large nuclei, it's a little bit weird, but at small nuclei, essentially you want to have like a roughly even number of protons and neutrons, right? Like the most stable version of carbon is carbon-12, right? 6 protons, 6 neutrons. The most stable version of oxygen is the same, where it's even and even. Nitrogen is like 14, so it's 7 and 7. Oxygen is 8 and 8, protons and neutrons. So if you have something like carbon-14, which has 6 protons and 8 neutrons, that's kind of unbalanced and that's not super stable. And so that may undergo a beta decay, and a neutron in that nucleus could turn into a proton. And so note that if it was 6 and 8, 6 protons, 8 neutrons, and a neutron jumped to the proton side, now it's 7 and 7. It's not carbon anymore, right? Because it's got 7 protons. So now it's going to be nitrogen. So it's going to change into a different element in this case. But it is worth noting that the mass doesn't change, right? Because protons and neutrons weigh pretty much the same. And so if you have one change into the other, but it stays in the nucleus, then like the weight doesn't change. It's one of the cool things about beta decay. The mass never changes, and you don't have to worry about that like at all.
Super quick, because actually something you said prompted a larger thought, so to speak. So make sure, because I really like that you mentioned mass at the end. I hear students confuse mass and weight just generally speaking for physics on the MCAT. And so remember that one is the applied gravitational force and one is mass. And so just things like that I know you emphasize in the course, and just being able to recognize the difference between the atomic number, the atomic mass. And you mentioned equations with this. And so if folks haven't already seen this, there are actual equations that show the different types of decay that you need to be familiar with how they're written, because the AMC can do something that's a little mean and show you the equation and expect, well, actually it's not mean, it's actually very fair game, but show you the equation and expects you to figure out what is happening, but also just show you a net equation and help have you figure out what has happened and multiple different types of decay that could have happened, multiple different steps to lead from one element with one mass to another element with a different mass. And so you have to be able to write out and identify and be able to figure out which types of decay correspond to which equation and which combinations of different types of decay can correspond from the change of one element to another. And I've seen that, and I remember that multi-step one being the bane of my existence when it came to the nuclear and radioactive decay, but something you want to keep in mind that is fair game on the MCAT.
Yeah. So like they could ask you like what must have occurred if we had some reaction and something, let's say, lost 6 protons, but only lost 2 neutrons. Like as it went through that. And a lot of students are like, wait, what decay is that? And the answer is it isn't one decay.
Yeah.
Right? It's a couple. In that case, like the best way to deal with that is to focus on the mass first, right? And so you went down by 8 total mass. And so the only way to change mass is alpha decay. And so you must have had 2 alpha decays go by, which means you lost 4 protons and 4 neutrons. And then you must have turned 2 protons into neutrons. And so now you have lost 6 protons, but you had lost 4 neutrons, but you got 2 of those back. And so now you've only lost 2 neutrons total. And so that would be like in that case where you lost 6 protons and only 2 neutrons after multiple decays, what you have there is 2 alpha decays, and then also 2 beta plus decays, because we had protons turn into neutrons, and that occurred twice. And so that's a way to kind of deal with this. Always start with the mass. Mass first, and then figure out like, okay, if I did the mass and got the mass right, now how many beta decays do I need to do, and in which direction to get the protons and neutrons right? But yeah, this is a big thing. You definitely want to be able to deal with this, and like you can have those cascades. This is also stuff that shows up all the time in medicine. We'll talk more about that. But there is one more type of, I should also mention like that, like some of these in beta decays can occur in reverse. And you can have like what they call electron capture, where it's like the beta minus decay is just going in the other direction. You shoot an electron in and it flips it to the other way. So that reaction can go backwards. I think that's the only one I've ever seen tested on the AMC. And as far as I know, I'm sure the other ones can go backwards, but I don't know if that's I've never seen or heard of it. I'm sure that some physicist is dealing with that. But there's also the gamma decay. And so gamma decay, I like to kind of think about this as just like the protons and neutrons in the nucleus. And this is a simplification, but it's good enough for the MCAT, so we're going to go with it. What happens in there is like you might have more protons on one side than the other, and like those protons don't want to be together. right? They want to be kind of evenly spread apart. The strong nuclear force is going to hold the nucleus together. But like if we have all the positives next to each other, they're all repelling, and that's not stable. Another name for that is high energy. It's a high energy state. And so what can happen is we can just shuffle those things around and move them around so it's a little bit more even. And now it's a low energy state. It's more stable. And like that's a much better scenario. But we can't just lose energy. We can't go from a high energy state to low energy state without like where'd the energy go, right? It has to go somewhere because of conservation of energy. And so in this case, we just have to release that energy as light, as a photon. And so this is why everyone's favorite decay is gamma decay, because in the nucleus, nothing changes. It's just a little bit more stable. And it emits gamma rays, which are light. So if I had carbon-14 and it underwent gamma decay, still carbon-14. Nothing changed there. It's just a little bit more stable now than it was a moment ago. Gamma rays, you should recognize that from the electromagnetic spectrum. Those are the highest energy photons. And so that's because they're from gamma decay. This also comes up in medicine a fair amount. And there are surgical techniques and things like that. But we should actually, I don't know if you have anything more to add about gamma decay. It's everyone's favorite because it's simple and like it's the nice one.
No, I think you said everything that, students really need to know. It was one of the, I think I mentioned to you this to you before, but it was one of the articles that was suggested to me just because if anyone is interested in this, scientists, early August realized that we have the sun has emitted energy in gamma rays stronger than we have ever detected before. And so it's something they're like, now we need new theoretical models for how this sun works. So there's always something. And if you're finding these topics interesting, you can absolutely go and look more into them. Just keeping in mind that what we're covering is nowhere near as much as what we know as human beings, but also it is what you need to know for
yes.
So you don't need to know how strong the gamma rays from the sun are for the MCAT. But who knows, maybe that paper will one day end up in the MCAT.
Yeah. So there's a couple of techniques that we could talk about. One of them, like in the realm of gamma, is gamma knife surgery, which is actually kind of interesting. Gamma decay produces these photons that are really high energy. And so if you blasted those high energy photons at a cell, we know that high energy photons can knock electrons off of things, right? And this is actually something we have to be careful from the sun, right? Like the highest energy photons goes ultraviolet, then higher energy is X-ray, then higher energy than that is gamma rays. Ultraviolet rays from the sun are dangerous to us because they will knock electrons off of our DNA and turn our DNA into radicals. And so that's why we wear sunblock, because we can block the UV rays from the sun. But gamma rays are even higher energy. And so a lot of people are like, wait, why would we blast this into somebody? Like, it seems like not a great thing. But what they do is they go in and they blast specifically cancer cells. So it turns out cells that are dividing are more susceptible to this damage than regular cells. And so you could send a bunch of gamma rays into a person, and what happens is you are damaging the cancer cells more than you're damaging the cells around. That's why a lot of cancer treatments actually mean you're more likely to get cancer in the future. And that's just like one of the way-offs or trade-offs that comes with a lot of cancer therapies. Is like, okay, we need to kill the cancer and minimize side effects. Another way they do that is they don't go in from just one angle. And so you can imagine sending like a weak, quote unquote, gamma ray stream in like through somebody. And then you could send in another one from another angle, and another one from another angle, and another one from another angle. So most of my tissue is getting like just one stream of those gamma rays going through it. But there's one point where they're all like going through that one spot, right? And that one spot, hopefully, cancer. And so you just like bombard that one area with like lots of stuff kind of going through there. But all the other tissue around it is getting a more minimal exposure to those gamma rays. So super interesting kind of in the realm of cancer treatments, gamma rays. And this is why nuclear medicine is a whole field of medicine. Like there are people whose entire life is nuclear medicine.
Yeah. And like you mentioned, this plays a role in cancer treatments. It can also nuclear medicine can also play a role in cancer detection. And so one of the things that you will hear about when you are a future physician in medical school, but also that is very fair game for the MCAT, is something called a PET scan. And so this is a positron emission tomography. So this should sound familiar from the conversation on decays that we just had. And essentially what they do is they take a essentially radioactive version of glucose, so to speak. And so it's fluorinated, and it's one of the elements that can be radioactively labeled. The mnemonic that I like for this, for radioactive labeling, is it hops if carbon. So I think of the like decay, whatever it is, hopping off. And then you have hydrogen, oxygen, phosphorus, sulfur. The if is iodine, fluorine, and then the carbon. And so it hops at carbon. And so one of the elements then in this version of glucose is radio-labeled. And that means that this radioactive tracer can be followed when they are performing this scan. And because it's glucose, you can imagine that cells that are very metabolically active, tissue that's very metabolically active, is going to light up more than tissue that isn't as not as radioactive, isn't as metabolically active. So this is preferentially going to light up cancer cells as well as other metabolically active tissue. But this helps us identify, hey, this tissue is looking a whole lot brighter than it's supposed to, than what it typically does. There is a higher probability that there is cancer here, right? Yeah. Unlike a lot of the other types of imaging that we do in medicine, which is often structural, this is functional imaging, which is really cool. If you think about, a CT scan or an MRI or an X-ray, it tells you what's there, but it doesn't tell you how what's there is functioning. And so that's something that is really helpful with PET scans. There are other types of functional tests, like a fMRI, a functional MRI, but this is one of the main ones that you need. This is one of the ones that you need to know for the purposes of the MCAT. You can also think about how it would be helpful not just in detecting cancer cells, but just maybe what part of the brain is more active than another, right? Because that part of the brain that's being activated, let's say that you're performing some math, some algebra, and you want to see what part of the brain is being activated. Theoretically, if you could get someone to sign up for this, you could figure out what part of the brain is engaged when someone is doing math. And that's another really cool application, but one of the main ones that you'll see it in is cancer detection.
Yeah. Of all the types of decay that we've talked about, like alpha, beta plus, beta minus, gamma decay, this positron stuff is probably the highest yield for the MCAT because of the PET scan thing, and like using for cancer diagnosis, and because it does show up in the psych-soc section with like imaging brain areas, like you said, like trying to figure out what's going on in someone's brain when they're doing math or thinking about their mother. If you're Freud and you're doing research, I bet he would love to do PET scans. But yeah, so that's a big thing. And it's basically just looking active stuff. And so they will do full body PET scans if they're worried about metastasis. And like if you have like a spot in your bone that lights up a lot in PET scan, that is a little bit worrisome because like bones shouldn't be super metabolically active.
Yep.
On the other hand, if your heart lights up, yeah, that's fine. Right, like your heart should be super active and like burning a lot of glucose and energy. And so it has to do with, basically they staple that radioactive fluorine onto the glucose when they dump it into your blood. But yeah, that's a big one. I also, like you did mention, like a lot of times we'll do like scans with contrast or things like that and like imaging different stuff. And so like having, there's different ways to do like contrast stuff, but some of them they will use radioactive labels like besides like fluorine, but those ones that you you mentioned are worth noting. The iodine one is actually specifically kind of interesting because like iodine builds up in your thyroid because you make T3 and T4. And so they will actually give people radioactive iodine as a treatment. Like if you have thyroid cancer, if I just put radioactive iodine into you, that radioactive iodine will go to your thyroid and start to kill off those cancer cells. Now, you will have iodine in the rest of your body, but it's really low dose because iodine like piles up in the thyroid. So it's often used as a way to treat specifically thyroid cancer, kind of like a weird, kind of cool overlap between physics and like biology, like therapies. There is also other stuff kind of like outside the realm of medicine. There is, so like in the atmosphere, right? Nitrogen is like most of the air that we are breathing, right? Like 70% of the air you breathe is nitrogen gas. Nitrogen has like triple bonds to it. So it's like really stable and doesn't really break apart. And so you take a deep breath, mostly nitrogen, does nothing, interacts with nothing. And it's just filler, essentially. But when that nitrogen goes way up into the high atmosphere and gets exposed to a lot more solar radiation or light from the sun, it can get converted into carbon-14, right? Now, thinking about that, like what kind of decay does that sound like? It sounds like, that should sound like a beta decay, right? Because we have nitrogen turning into carbon, so that's a change in element. So that's definitely not gamma decay, but also nitrogen is usually 14 and it turns into carbon-14. And so carbon-14, the weight didn't change. That's like a beta thing. But this happens pretty much constantly all the time. And so the amount of carbon that we are breathing in, that like, breathing in from the air, the amount of carbon that is carbon-14 is pretty much constant. Because yes, the carbon decays over time, but it's being replenished by this nitrogen interacting with the solar radiation. And so plants that build glucose out of the CO2 in the air, they're taking all this carbon dioxide and building stuff out of it. And so as a result, a fraction of the carbon in that plant, let's say like soybeans or corn or tomato, a fraction of the carbon in there, and it's pretty even, constant fraction, is going to be carbon-14. And it stays pretty constant because it doesn't decay. I think it's like a little over 5,000 years is the half-life of carbon. And so if that plant died and I buried that tomato in the ground and like it should have a certain amount, let's imagine somehow this tomato isn't going to rot, but so things are falling apart. Let's say an animal eats the tomato. Now they have that amount of carbon-14 and then they die and they get buried. So you could dig up this animal years later, and we should know that, don't hold me to the math here, right? This is way too high. But let's say I know every animal on the planet, every plant is about 10% of their carbon is carbon-14. Inside this animal that I just dug up, it's 5%, right? So that means that 5,000 years must have passed because the amount of carbon in there got cut in half. And as long as you are living and eating food, then you are going to be replenishing that carbon-14. It should be pretty stable in your body. But once you stop eating carbon, aka you're dead, then all of a sudden, like you will still get this really slow decay rate. And so you can kind of figure out how old things are based on how much carbon-14 is in their body. And so this is carbon dating, which gets used all the time in science as well. And that also has to do with this beta decay and also half-lives. We haven't really talked that much about half-lives, but different things will decay at different rates, like going through alpha or beta or gamma decay. Some things have half-lives of, like years or decades or centuries. Some things have half-lives of like incredibly short amounts of time. Depending on the element, I believe there are some that are femtoseconds, to talk about like very short measurements. Those are things that we're like, they don't really even exist, these elements in like natural states. It's just because the moment it's there, it's gone. It decays so quickly. But yeah, all of those are things definitely to kind of think about. There's a lot of stuff here, and there's a lot of cool science in the world. And so hopefully you guys can see like how this, a lot of times I'll have students come to me like, why do I need to know nuclear physics? Like that is not something a physician needs to know. And it is absolutely something a physician needs to know if you are going to go into radiology, right? Like that is all they do, nuclear medicine, cancer medicine, like all of this. Even as just like a general practitioner, you will be ordering PET scans. You will be ordering different techniques and for treatments and for diagnosis. And so like understanding those is really important. But there is some cool stuff out there that we're like not going into. Just one plug, just because it's super interesting. There has been some experiments in the last like 2-ish years. One in particular from the NIST that has been repeated a couple of times that seems to imply there is a fifth force and everyone's freaking out like in the physics realm because they're like, okay, we've done this experiment. We've accounted for all the forces. There's still a force. Like it's not any of the like strong or weak nuclear. It's not gravity. It's not electromagnetism. We don't know what this force is. And so everyone's kind of freaking out there. So that may be changing in the future as we learn more about it. And we are starting to get to that kind of cutting edge, right? The nuclear fusion stuff is stuff that like getting more energy out than we're putting in is something that is also relatively new to the last couple of years. There are a bunch of people that are going to be winning Nobel Prizes here in the next couple of years based on like these science experiments we're talking about. And it's really interesting because it's always like at first it seems like this is not going to be useful to medicine or things like that. If you think about the atomic bomb as like, why is that useful? But now like PET scans and gamma knife surgeries and like all of these things, like those are like now like a big part of medicine. And so who knows, maybe we'll find out what that fifth force is and maybe it'll be really useful for diagnosing or treating something.
Yeah. Really quickly, folks, just a really quick reminder. It is important to understand these things conceptually. I know I've said it so many times, but they're, like you pointed out, Phil, this could come up in the chem phys section. There are relationships with biochem, and that's fair game in that section as well. Toss in some psych soc. So even though it may not always feel like it, this material is pretty high yield. And I really enjoyed talking about physics with you because it's not typically my jam, but I always learn something and you make physics interesting and fun. And that's what learning should be. Learning should be fun. And that's something that we really strive for here at Jack Westin, just to keep you all engaged. And so hopefully you found this podcast episode to be interesting and maybe it inspired you to go find out, if it hasn't already been by the time you get there, what that fifth force is.